Okay, welcome back from spring break. Okay, so today we are going to talk about regression and regularization. So this is a week number 9. Okay, next week we will have a guest speaker, and he will be here. He's my postdoc scholar in my lab. Oh, there he is. So yeah, we're talking about you. So next week, Dr. Salim Romero will give us the lecture Tuesday on the decomposition of matrices. He has a very strong numeric computational biology background and from a physics, chemical physics background. Okay. So Salim, you can just log in here and switch it on. Use your net ID next Tuesday. Okay. Yeah. Okay. So. Salim, are you going to use the slides I had prepared for, or you want to use your own for next week?
I haven't decided yet.
Yeah, okay.
So far it looks like I'm going to use your slides.
You can, yeah, but you are welcome to use your own,
Okay.
because there are different ways to convey the same information. So all we have to do is just make students here and understand the SVD and decomposition of these matrices. So we know how to do this matrix multiplication from almost day one. We learned this. Everything is to do this dot products, matrix multiplication. We will do a lot of today as well. But next week we start to have the product, have this results of the multiplication of matrix amount to decompose, to open them up, to make them into different components. So that will be the next week. So this week, we will discuss regression, okay, methods. Then I don't know how many of you understand this regularization, also lasso. Anyone know a lasso? What lasso is? Okay, so that's for you, okay? Then we will also use regression model to do highly variable gene detection. There's applications in single cell data analysis. It's a directly application of the regression models to find those genes highly variably expressed in a relatively homogeneous population of cells. And then you will realize what's the meaning of those genes which show extremely high variable in their expression patterns. Okay. Sometimes people call it gene expression noise because you cannot predict very well and which level of this gene will express in next cell. So that's there also the function is very important. Okay, so I don't know if you had previous knowledge or experience or impression of what regression is. So you may, on your mind, have this picture and scatter plot with a line goes through this data points. Okay, so you may use Excel spreadsheet, some add-ons that you can do this kind of table, and you get estimates, those values, and p-values for each of these coefficients. You may also know this squared relative residual squared errors, those things. And if you used R or MATLAB, you may know, okay, there are regression functions you can call and to do the regression. So that's your impression normally have as a background of the, with normally biology students. But putting this into the more generalized picture of the machine learning, so you know regression is a supervised learning approach. What that means is you need to train your model. So what the model is? Model is your understanding this trend of the change of the variables and also preset their values by using the given training data. So you need to have the training data, you have your scatter plot, okay? Then you train your model. You know this straight line should have a slope positive or negative depending on your observation of your training model. So that's why it's supervised learning. You have these models will be trained by the way of this given training data spread it, and then you have it set up your regression. So more generalized expression is like this. You have a regression function, f. So this f will take, so in this 2D scenario, you have your x, you have your y. Y is your response, so you have input and you have your output. So this function is a regression function to give your y prediction value. So once you have this model established, so next time when you have a given x value, so for example, this will be given and then your expression, by putting these values into the function, you will have expected y values here, okay, based on that model. So those blue dots are the training data, and this pink one is the new prediction you want to make. So normally, this prediction is not accurate because you expect some errors, so it's not exact. So you have this approximation. Well, this x in our example is 1D, and then y is 1D, so this whole system is 2D. However, you can have this more generalized, make this high dimension. So you have x1, x2, x3, or xn combined together to predict a single output. Okay, so this is a more generalized expression into to turn this regression problem into an optimization problem. So this looks like very awesome expression, but it's a general form and formula in the optimization scenario. So you try to minimize expectation, which is between the difference between this and that. So this is a loss function. So L means loss, okay? Loss means if you cannot predict y very well, so you lost power or something, you missed. So this is called a loss function. And then loss function takes two inputs, the y, and your estimation of y. So there's a difference between them. So you want to have this loss function value minimized because you want to use this to approximate y. So make these two very similar to each other. So that's where you have this. You want to make the difference between them the difference between them as small as possible. So let's minimize this expression. Okay. So basically, that's what the equation is about. So the most commonly used loss function is just this. So it's called the least square, which you just use your predicted value of y minus the real. You know it because it's training data. You know you need to approximate your function to predict y as accurate as possible. If you can predict this very accurately, so the difference will be 0. And then you minimize this. Okay? So this is called the norm. Okay, you know the norm, L2 norm, and then squared. Any questions so far? No? It's okay? Very easy, right? So we jump back to one even easier, and we revisit again and again. Dot product and the norm with a star in the norm. So that will be the L2 norm. So I just want you to know the dot product x and y will be equal to x1 times y1 plus x2 plus y2. Okay? So that's the expression. So come back to our dot product definition and link back to this regression equation. For this, we need two vectors. We need a vector beta, okay? So this beta is like this. Beta 0, beta 1. So I'm using a 2D simplest linear regression as an example. So we have a vector beta, and then we have another vector x. So x is your input data. So here we have only one input data. So now I'm going to write in horizontal way in this 1x, okay? So x1. So that means our input. So this is our input data, x. Remember this function, x, and we try to predict y, okay? So this is our input. This input only contains one variable, x1. If you expand this to x2, you have to increase the beta value into the same dimension as well. You know, if you do this dot product between this x and the beta, so this dot product beta x will be a single number, right? Right? Even you use dot product, matrix multiplication, whatever, this will be a single number. So this single number equals to beta 0 times 1 plus beta 1 times x1. This single number is y, we predict. So if you write them out, this will be y equal to so beta 1, beta 0, x1. So this is a regression regression line here. So you expressed in a different way will be transpose beta and times x, or other way around, you always get this value here. So in this case, it's a 2D case, okay? So you want to use two variables, x1, x2, to predict your y. Same way, you multiplicate by the beta vector, and you get expression like this. And this expression, again, same here. So that's a 1D and a 2D, whatever. You have a very generalized formula, which is your prediction. The prediction y is the dot product between beta and your x input. So this is regression. So beta is the coefficient. Beta contains beta 1, beta 0, beta 1, beta 2, depends on how many variables, what the dimension of your input variable sets. So beta is a variable. You can change, you change the value in the beta. You don't change the input, because that's your training data. You change your beta values to give different predictions of y. You try different combinations until you get y is the result of this dot product approximate with y, okay? So for this, I wrote into this vertical vector, but in the next slide, I'm going to make it horizontal, just like here, okay? Make them horizontal, and also expand into not only 1, 2, but maybe larger variables, numbers. Okay, so another concept is this norm. And also there are geometric expression of this norm. So we always talk about L2 norm, that is the distance. If you have a variable, so this should be 2, okay? There's a typo here. So if you have a set of this variable in your vector, the norm of this vector is this data point distance to the origin. So that's the magnitude of this. So if you have the restriction, say, okay, this expression, this norm has to be 1, so then you will have a circle, so unit circle. This is a 2D, so you have x1, x2, but you have, if you have high dimension, that will be a sphere in the hyperspace. Well, L1 norm means the sum of all the absolute value of those variables. So if you have 2D scenario, then you have x1, x2. If I say, okay, your L1 norm of your vector, so there are two numbers, has to be limited into the 1. So you will be, or smaller than 1, you will be located within this square. Okay, this place here is 1, 0, and here 0, 1. This place will be 0.5, 0.5. So the absolute value of those variable and the values and the sum together should be 1. So you would have to be within this region. It will be the valid distribution of your variable combinations and within this parameter combinations within. If you have L2 norm restriction, then your vector or your combinations of the x1, x1, x2 has to be within this region. So that's put them together. We will use this concept to do this lasso when you have select the combinations of the variables with a restriction. Okay, so we just put this concept here for now. Come back to our regression equation here. A concept here is if you are talking about a simpler linear regression. Simple linear regression, we only have one variable to predict y. And the beta 0 always put here is like intercept of this regression line and push the magnitude of whole system to a certain level. It's just like a value help you to centralize your data. So when we have the simple linear regression model, we are talking about there's only one variable to predict your y, okay? But most of the time, we are talking about multiple linear regression. The formula is still linear form, but the variable name values, the number of variables increased. Not only one, but you use n different variable to predict the outcome of y. And each variable has its own coefficient. Okay, so they are independent variables, vectors, and then you have a dependent variable y, and you use the beta. Coefficient values to tune your model to make approximation. So this is called a multiple linear regression. Example is like this. So if you have a system to predict the price of a car, and you only use the engine size x as your model, then this is a simple predictor, and this is a simple linear regression model. Then you tune your parameters, and you found that this beta has to be 156.9 times the engine size. So this numbers come from the training data. Okay, so you observed a lot of models, and with the cars have a different engine size. Then you make this prediction model. Well, for the multiple linear regression model, you have so more than one. Okay, so in this case, you have 6 different variables, and their combinations will be used to predict one outcome, which y is the price. Here we have height, width, length, and peak, RPM, etc., and put together to predict your price of this car. And by combine these variables into a different weight, this weight will be given by the beta values. So this is multiple linear regression. Okay, so this will be the most cases because we do this multiple regression model more to understand the system. Same thing here for the single cell data. So you probably want to use more than one genes to predict a single state values for the whole cell. Okay, so you don't want to expect to have one gene to predict what this cells in which state, which the state will be expressed as a y value. But normally you want to use more than one gene and also combined. Okay. Okay, so this awesome expression is what I discussed here. So I write the input x horizontally. So remember, this is one data, one input data. And after you have this parameter, coefficient parameter, and then you will compute one single output. But if I expanded this input data into more than one input, then I have another one. So this x, still the first variable, so, but this is the first variable, sample 1, so this is sample 2. So I can add this first variable sample until n. So I can expand this into more than one input. So here, the whole thing will be big X in a matrix form. This contains n samples. So we are going to train the model with not only one single input, but multiple. And my example is only just one variable, but if you expand this to multiple linear regression, then you have x1, x2, x3. Okay? So x11 means the first variable, the first sample. x12 means first variable, the second sample. Well, if you have x n m, that will be the n variable m sample. So the whole matrix is your input data. That's what we have here. Okay. Okay. The subscription is slightly different with me and what I had. So the 1, 2, 3 in the front, that means the sample. So 1, 2, 3, 4. In the car example, that will be our first car. Could be Ford, and this of Toyota, maybe different brand. Okay, each row. And then column will be the engine size, height, weight, the variable. So that's our input. So for each car, you have output. That's the price, y1, y2, okay? To make this work, you have one input. Depends on how many variables you want to use to make the prediction. Depends on how many, in this case, there are p variables. In our multi-regression car example, there are 6 variables about the car in order to predict the price. So in that case, there will be 6 variables, and how many cars depends on your sample size. Okay, so once you have the p decided, you use 6 variables to predict the car price, then your coefficient, the dimension will be fixed. So the beta will be the 6 variable changeable parameters, okay, the beta value, in plus the intercept, beta 0. So that will be p plus 1 variables. So that's the general formula, and you use the matrix as input, and then your beta is vector. So this matrix is n by p plus 1. Your vector is p plus 1 by n. Okay, so you can make this matrix multiplication. The output of this, the size will be n by 1, the same as your y. So you want to use this to predict y, but not be able to predict it perfectly, so you have to add a error term. So this error term will be the difference between your prediction and the y in your training data. Any questions about this? Because from next slide on, I will not going to give you the whole write-out of this matrix. I will only use this matrix multiplication with this symbol, the variable. But you have to be very clear, and this is a matrix, contains all the input data, no matter how big this is. Okay, you have millions of samples. The same equation compared with you have 2 or 3 samples. But we are going to use small 3 samples normally as an expression illustration examples. Okay.
Is that E is bias? I mean, is that an intercept or a loss function?
Which part? The beta 0?
The E part, because
Yeah. So this place, I don't believe you have this because once you do the multiplication, it's become 1 to n. It's 1 to n, so it's the same size as your y. So this will be n instead of p plus 1. So the size of this beta and this is very different. Okay, so once you have this matrix, you have a beta, and then you know the dot product for each. Then you can write in this way to do your calculation to get the training y output.
why there is a beta 0 in all the rows? We can just
Beta 0 is required if you have not normalized all this beta 1, beta 2.
but it will be constant for all the rows, right? So we can, I mean, basically that information will be redundant.
This beta 0.
Yes.
If you see this is redundant, then beta 1 is also redundant because they are all the same.
But x1 and x2, I mean,
Oh, this is different.
yeah.
Yeah, I think you can see, okay, I will minus beta 0 from my training to centralize all the outcome, all the price. You can see, okay, I minus the average. Then your car price, instead of 20,000, you may have something in the positive, negative. It's okay. Yeah, you can do that. Yeah, intercept. Okay, so this is an example of 2D. When we have a 2D which is greater than 1, then we still is a case of multiple, multi-variable. Variable means your x1, x2, you use 2 variables to predict y, single y, okay? So this is just the number of the index of your observation. So this, you have 17 training data. You have x1, x2, and you use these 2 to predict y, okay? Your beta will form this plan, and then the beta value after training by plugging in those, and you found this will give you the minimized difference between your prediction and overall, okay? So that's a solution visually. I want to bring up this very confusing terminology. when people see univariate analysis compared to multivariate. So this is not a multivariable analysis. When you see the variant, especially when we talk about multivariant, we are not going to cover this any further, but I just mentioned when we talk about the multivariant, it's very different from multivariable, but because multivariant will have multiple output. Okay, so input is maybe the same as what our multivariable, multiple variable regression. But the output, if your output is not a single Y, not like this, like price of the car, but you have more than one column of your output, this become a multivariate analysis. So our all we talk about univariate analysis, because output is always a single variable Y, rather than compound variable y1, y2, y3. So we have univariate analysis including multivariable regression, because multivariable means you have more than one input. But as long as you have one output, you are univariate analysis. Okay? So there are paper people discuss about simple regression. Okay, single input, single output. Multiple regression, or multivariable regression, have more than one. Okay, engine size, weight, length, everything, to predict the price. Single output. As long as you have multiple output, so Y become not a vector but a matrix, then this analysis is called multivariate analysis. Multiple, multivariate, they're multivariate regression analysis, but not covered by this lecture. Okay, but you need to be very careful. Okay, when you write your thesis, never write multivariate. I'm doing the multivariate analysis. People who know statistics will know. Okay, immediately triggered their nerve and see. Okay, what's your more than one output Y? You predict the matrix out. But don't use this if you don't understand. Just use multivariable. Okay. Okay, so linear regression. As I mentioned, we are not going to write out all this matrix representation, but only use symbols. This X is a matrix, and the beta is a vector of the coefficient, and this beta is intercept, and this is a formula, and here is dot product between each sample, each row, with this column beta vector to predict single value of Y, because it's one each time one row, and depends on how many rows, how many input samples you have, you predict how many output. Everything is dot product, and the X0 plug into this matrix in order to make the intercept. Example is like this. I have 3 inputs. Okay, my 3 inputs is -3, 0. Okay, you can replace values here. Use real examples. three rows, intercept is always here, so negative 3, 0, so because that's my first sample, is that point. I have a second, 0, 2. Okay, I have a third point, 3, 4. So this make it abstract from the car example. So this just variables. Okay, so this x and this y. I think this is. I need to just express this because that's why we try to express. We try to approximate. So I want to use this input, the single variable, to predict the y. So the y is, I have a 0, the first 2, and my 4 is, so this is my y, okay? So to do this, I need to adjust the values of these two in order to achieve, I need to make adjustment for beta 0 and the beta 1 in order to make the input. If you have 1, if you have 3, then you have 4. You have 0, you have 2. So you need to solve the problem of this, okay? And then you can get the values. So how to solve this? If you have a perfect situation, you have no errors. You have your input, active 3, 3, 0, 3, you output 0, 2, 4. In this scenario, we are going to compute the beta by using the matrix inverse, okay? You see, this is a matrix, and this is beta, and this is y. So we know for the training data, we know the x value, we know the y. The only unknown is beta. So if you can see, okay, I can rearrange this formula and put, if the integer, then you have a y divided by x, okay? Let's rearrange this. But for the matrix, you cannot do this. You need to put beta times y, okay? So this operation is inverse of a matrix. So what is inverse of matrix? So we found it's inverse by, you know, a matrix multiplied by its inverse is identity matrix. So that's the inverse. So if you know how to compute the inverse of your x, it's very easy to compute the value of beta. If you just inverse your x and times y, you get the results. So for our example, so this is a changed example. It's not like the one just right into, but the same idea. So if you have 3 points, okay, you have 3 and give 4. 1.5 give 3. Negative 1.5 give 1. So if you have this, you have x and y. You just need to inverse this x and you get the y value. Okay, so this same expression in MATLAB. Okay, so that's in the Julia. So you compute the inverse of x times y, you get the beta value 2 and 0.66. So what about if you don't have a perfect input and output? So you want to have a straight line go over the majority of the center of these points to minimize the difference. So the difference is your training data and the expected data. So that this yellow bar is the difference. You want to have the total difference as small as possible. So this is called the least square loss function. So to do that, we at the end, so this will be still the solution, okay? Even though our example is perfect straight line goes through all your input data. So you know you can compute your beta using this formula. But even you don't have a perfect situation, okay? You can still use this formula to compute. There are theoretical solutions which will lead you point to you the same results. So what's the expression of this least square formula optimization problem? So we have input x, okay? Now it's right into this small variable name with subtraction. Okay, so this x, y, you have a j different variables. So those are the n number of samples. So if you look at this carefully, this is a dot product, the whole thing. Okay. The whole thing is this, okay? Plus your intercept. Intercept is the same as everything in the dot product, so you just add 1. You can put outside. But this expression is the same as that. Okay. So now the difference between them is that your prediction. You predict accurate to that, then this difference will be small. It doesn't matter you're over-predicted or under-predicted because you have a power 2, so even you have a negative 3, you will be 9. Positive 3, you will be 9 as well. So you just need to minimize the deviation, okay? So not only consider one sample, but you have to consider the total, okay? You have n different samples in your blue points. In this 1, 2, 3, 4, 5, 6. So in this case, we have n equals 6. You have to consider them all together. So you combine everything. So this squared, this squared. So you want to make them as small as possible by changing the value arguments of the beta 0, beta 1 until beta p. So that's the variable coefficient values you want to make change in order to minimize the whole thing. Okay, so that's a solution in the beta hat. I hope you can explain this yourself. If you next time you see on the textbook or papers, you will see this a lot actually in the supplementary files in a lot of this bioinformatics literature. Yeah. Yeah.
The reason why the square is taken,
This one here.
that prediction is
Uh huh.
the square of the difference is taken. Is it so that like we're trying to minimize the errors, right?
Yeah.
So if I'm making sense, is it to like punish the large errors? Like
It's some kind of transformation to, yes, punish even larger because you squared. Yeah. You're right. Yeah. So if you don't take squared, you can use absolute value. You probably will get the same solution, but somehow penalize this. If you have a large error because you're squared, you get more punish in your overall loss. That's right. Yeah. Okay, so this part is to let you to understand, okay, so even though you don't have a perfect straight line go through all the training points, but you still have the solution like this to give you the best minimized overall. So what's this? So this is a residual sum of the squared. Okay, so for the any given beta. So you try different combinations of beta. Every time you have different of this total difference squared. Okay. So we want to minimize this RSS, the residual of sum of the squared by given beta. So this expression can be rewrite into this formula, okay? This is dot product between them. Then the whole thing will be involved in this. So what to see? We need to have a differentiation. Okay, so with respect to beta. So so this beta function is related with beta. This somehow is quadratic. So you need to find the place where the change of beta. Change of this beta, the slope of change of this beta value, because this is a function of beta, has to be 0 in order to give you a minimized solution. So there are some of this differentiation formula involved here, so I'm not going to go too much details. You can have a YouTube video as a reference. But this solution will be when beta satisfied this situation, you will get the minimized beta, okay, to give you a minimized RSS value for this set of beta. So you can move this part to the right side of the equation, then that's a solution of a beta, which will give you the smallest RSS overall. This is another expression, same idea, and it's just right into the omega or W start here as a beta, okay? It proves that beta should be this formula, okay? Or you can write in this formula, okay? They were the same to give you a solution. The way to solve this is this beta, this RSS value function expressed in this way. Then you have the derivative of this, the gradients of this. This is theta. Then so this is a derivative formula. Then through this process, okay, you can get at the end this epsilon smallest value will be given when you have W, that's beta, equal to this. So I do have this write out, but I don't believe you really need to have that, because it's very similar to this and that, but I just write in my own way. So this RSS is epsilon squared, dot product between them, and this is a difference between your prediction and predicted value. You can use dot product, all the terms have been written out, and when you take the differentiation of respect with beta, and because this term has no beta value, so it becomes 0, and this becomes that. Follow this this given differentiation formulas, and then you can get all these derivatives, and then simplified. If you need this to be 0, so you put 0 here, and in that case, this beta should be something like this at the end. Okay, so this is the solution for beta. Okay, so just like we had this, but our most stable expression is you have x transposed times x, then it's inversed times x transformed, then times y. Okay, those are the all matrix multiplication or matrix multiplied with a vector. But as long as you do this, you will get your beta. And that's the best solution for your regression coefficient combination. So there's no much difference between this and that. The idea is you use the beta to approximate y, then you can compute beta by y divided by x, right? And then because the matrix get involved, you have an inverse of matrices. Okay, I think we can take a break. Let's see the time. Yeah, 5 minutes break. Nice. Okay, I think everybody is back. So just remember, this will have the name. So this whole thing is called a normal equation. So that's a solution of the beta values. The combinations of a lot of values in there will be let you get the minimized epsilon squared, okay? So that's a solution for your regression coefficient. So we will try, so this is a normal equation. So we will try using real data points to play with these combinations, okay? In the computer session, you have an x and transpose multiplied by x itself, the matrix multiplication. The inverse, and then transposed x times y, and put them together, you get a beta. So we put them into test. If you have a 3 real perfect training data, and you can use this equation to get the beta value, which is the same as use the different ways. Especially in MATLAB, you have this backslash, okay? So you have beta. You know you can have this formula, but there's a shortcut in MATLAB. It's backslash y. This operation, because you use this so extensively, so MATLAB invented a new operator, okay, to backslash, and you very quickly get beta. So you can see x backslash divided by y, and then the same results as you use this full normal equation expression, inverse x transpose x times x transpose times x times y, you get a beta value. So this is called an inversion of the A, but they use so-called a pseudo-inversion operation. There's a special function called a PINV. So normally people use INV function to do the inversion, but PINV numerically more stable inside their SVD involved. So SVD, Dr. Samuel Romero will talk about next week. The P inversion to replace the real inversion, the numerically more stable for extreme values in the input matrix. You can write to solve the problem of the beta. You can use normal equation. Okay, that's normal equation. You can replace inverse function, use the P inverse, same result. You can also write this exponential -1. So this is just invoke the inversion function, same expression. You can do this as well. You can do SVD and do this P inversion, but more explicitly using SVD to get this. You can use the backslash division to y. So every expression here, you will achieve the same answer of the beta. It will be the same as you write utilizing the built-in function in the fit linear model, xy, and you give the expression. Okay, this will also get the same answer. There are many different ways to do this linear regression. Depends on the situation, okay? So the limitation of this. If you compute this directly, it's computationally expensive. The bottleneck of the computation is this inverse. Okay, you need to have a huge computational power for the large input data. So we can solve this more generally inside the real function inside here, for example, the built-in function to fit the linear model. The real solution actually depends on the optimization function, which another set of the whole numeric computation problem. So how to minimize, not directly use this formula. So this is for teaching purpose, okay? In real computation, inside what happened once you gave the computation, the built-in function in statistics toolbox, it will use optimization formula to minimize the difference, okay, just like this, but using optimization algorithms. So what's optimization of algorithms? I just use this as an analogy. So you try to optimize the sound, okay? So you have so many different buttons. So you just tune this, and there are different combinations. What you can do is just start with a random place, and then you tune the different buttons and ask your audience, is this better? Or if they say no, you reverse back and change another parameter until you put all the parameter into their position, and then all the audience, okay, this is really good sound, then you stopped. So this is a process of optimization. You just adjust, make a small adjust maybe each time until you reach some stable scenario or very satisfied function, cost function or likelihood function, whatever you call it. You have some stop criteria and you stopped there. So this process is optimization. So in our regression applications, you want to least squared function, you try to minimize all this and you stop. If you have objective function, our objective function here is a least square function. If you have a optimization which your object function is try to maximize something, you can put just a negative sign in front of the function. You will search for the negative, the smallest values, because most of this algorithm will search for the minimum values of your cost function. So if you want to maximize your cost function, you just put a negative sign in there. So this is a procedure just as described. We have initial guess of parameter combinations and evaluate with the function, evaluation function. Then if it satisfies the condition, then that the solution is combinations of those parameters for this problem. But most of the time, your initial guess will not give you the satisfied solutions, so you have to find the optimization steps to change, make a change of the parameter values using certain rules, and then try again to evaluate it until you get the satisfied solutions. So this iteration is the optimization procedure, but most importantly, how you optimize your values. That's where the different optimization algorithms differ from each other. So there are many different methods and gradient-based search. They try to find the gradients on the landscape of the combinations of the parameters. You try to find the gradients and move downwards. There directed search, okay. This is how to use, for example, the minimum search, function minimum search optimization function in MATLAB. There's a minimum with a boundary, okay. You set up, you have to search between 0 to 1, then you set x1, x2 as a boundary between the solution will be in there. Otherwise, this is a global search. You don't have the boundary. You can let the algorithm to search all the possible values. MATLAB have an optimization toolbox. I will play a video for their introduction. It should be quick
Optimization Toolbox
to load.
provides solvers for finding a maximum or a minimum of an objective function subject to constraints. This enables you to find optimal designs, minimize risk for financial applications, optimize decision-making, and estimate parameters. You can use the problem-based approach to define the optimization variables and their bounds, set the objective, and then solve. On this problem, the solve function recognizes the problem is nonlinear, applies a nonlinear solver, and uses automatic differentiation for faster gradient evaluations. Optimization problems often have sets of variables or constraints, like in this production planning problem. You can define arrays of optimization variables and constraints and index with numbers or strings, resulting in readable and compact representations of large problems. You can use the problem-based approach even when some functions are not naturally expressed as optimization expressions. This problem's objective function requires solving an ODE. We can convert this to an optimization expression and use it in the problem to be optimized. You can add integer constraints to linear problems involving variables which must take on integer values. This includes when the variables represent a yes or no decision, like whether a process is assigned to a processor in this scheduling example. In addition to solvers for nonlinear, linear, and mixed integer linear programs, Optimization Toolbox includes specialized solvers for quadratic programs, second-order cone programs, multi-objective, and linear and nonlinear least squares. You can quickly solve large and sparse problems with thousands of variables. Here, a quadratic problem with over 40,000 variables is solved in around 30 seconds. As an alternative to the problem-based approach, you can use Optimization Toolbox with the solver-based approach. After representing your objectives and constraints as MATLAB functions and matrices, the Optimize Live task helps guide you through this approach by indicating where to select a solver and insert your predefined MATLAB constructs. Optimization Toolbox works in conjunction with other MATLAB tools. You can accelerate numerical gradient calculations using Parallel Computing Toolbox. You can compile your applications into apps or libraries with MATLAB Compiler and Compiler SDK. You can generate portable and readable C/C++ code to solve your optimization problems using MATLAB Coder. Use this code to deploy applications to enterprise and embedded systems. For more information, return to the Optimization Toolbox page or choose a link below.
Okay, so all you have to know is there are a huge framework, and for you to, if you know how to describe your problem into a solvable cost function, then there's some engine will help you to find the best combination of parameters to solve the problem. So the most important part is you understand the whole framework and you know how to formulate your problem into a cost function. Okay, that's the center of the optimization. So you don't have to care exactly how this optimization algorithm will search for the combination values to solve your problem, but this is some introduction of this, how they did inside. So you have combinations of two parameters, for example, x1, x2, then your y is how high is your likelihood. So you want to search for the combinations of your x, y. So you want to minimize the likelihood function or cost function. Then you have to find you start from somewhere random. So in this case, you start from, say, 10, 10, 10. Then you move towards the slope, which gave you the quick descent to the a minimum value here. So you move, try this combination, try that, try this. And when you try this, this could be 7.5, 7.5, somewhere in the combinations. Then you compute the slope and then go down again and again. So this is the way you have to have a way to compute the gradient. Okay, this is called a gradient descent algorithm. You have the learning rate, so the alpha is bigger, then you jump to next combination values with larger step. If you have a very small alpha, you will move very slowly and very smoothly on this landscape of the gradient descent combination, parameter combination landscape. So this is within the gradient descent algorithms between, so there's a loop. You will keep moving, keep moving your combinations of your parameter. In this example, we have two parameters, so that's a 2D, and then the z-axis is the 3D is the cost function values. So you move on this 2D landscape, try to minimize the cost function. So you do this in a loop until you reach to the lowest value. There's no way you can improve your theta combinations. Then you return, that's a bitbased combinations. Okay, in the middle you have to compute respect to the theta and all the gradients, okay, all the slopes for, depends on how many parameters. In this case, 1, 2, big N, you have N variables. Then you have compute all the gradients to the different dimensions, then take them into account. Then move to your next step until you reach to the lowest values of your cost function. So this is a cartoon example. We start from the combinations of W and B from this place. So in this case, you have B -4 and W -3 somewhere in here. So the cost function gave you the value 13.5. Then you move, compute respect to the B and the W and the cost function. Then you move to that vector direction because that gave you the slowest, the next move to the lowest part. Then you keep moving, and every step you recompute this slope or gradients respect to all the dimensions, then from the shortest part towards the center, which this place you have 1.5, which cost function is much smaller than 13.5. So you stopped here. There's no way you can move anymore. Okay, the learning rate, as we mentioned, alpha, you cannot have a too big jump. Otherwise, you are not following this landscape very closely, so you get some random solutions. Well, if you have too small learning rate, you will have to do this iteration of computation of gradients a lot steps, which you will make the algorithm slow to converge, and you may also trapped into this local minimum. You don't find the global solutions which give you the best. You're trapped here because you move too small steps. The relationship between gradient descent with the Newton's method, people discuss the difference between them, but they are very similar in my case. Now the problem of overfitting, the problem, okay? So if you have only one variable, then you can blend that. There's no overfitting problem. You don't have many variables to explain your variability in your output. But if you have, say, thousands of the variables, their combinations can be fine-tuned by this large number of beta, because each variable as input, you can have a weight of beta to tune this contribution. But if you have many input variables in order to be used to explain, to predict your y, then you have a big freedom of the choice of your coefficient values. You can make them very accurate, okay, basically. Something like this. If you predict the price with this is your samples, okay. If you only use one variable, then you only one seed make change. You can have a straight line. But if you have another variable, so you have a slightly better term, so you get a better fit. Okay, use some kind of nonlinear term. But if you introduce more variables, then you get some overfit problem. So this looks very good for your training, and because every single approximation for each of the input data will almost perfect. But this model is not very good for predict the new data points. So we need some balance between not overfit, not underfit. Utilize this just alright model. So this depends on how we select these variables, and also how how to pick out the most informative variables, and get rid of those which contribute too less to the prediction. Same idea, how overfit for the this classification problem. Okay, so if you have this and this underfit, you have false discovery, so false classification. But here it's just all right. But here you have take care of too much of those outliers, then you overfit your data. But this model may be not very useful, but compared to this model, which select the correct number of this contributing variables to be included into the model. So our problem here is, if you have a large number of input variables, how are we going to wisely select those ones which make real contribution to your model, but not reduce the number of these effective features, okay? Not overfit your model. There are many different ways you can do stepwise selection. You can try every single variables. See, okay, my price of car, and I can use engine size to make prediction, and that will be how much contribution I can give weight for each variables. And at the end, I just select those most important ones. There are also other way to address this overfitting problem. So this is called regularization, okay? So that's a term come from. That means you can have a lot of variables in this n variables. N could be a big number in our single cell data analysis, maybe 6,000 genes to predict a cell state. See, the cell is in the which development stage. You can have values, see, 15, and another cell is 25, something like that. You can have make a prediction using many genes, but not every gene contribute equally to this regression model. For example, if you have a situation, the slope will always contribute, and also the first variable the coefficient is 0.03, very small, which the second one is 2.8. So you have these beta values. You want to have a way to select those important ones. This is a procedure is called regularization, and you put the smaller values into 0, or they keep the value which is large enough unchanged. So if you use this regularized version of a beta to do the prediction, you effectively you actually remove the sum of this variable, because a lot of variable will be set into 0. There's no contribution. You can exclude them from the modeling. So that's why you regularized the contribution of those, only keep those variable contribute the most. In our gene expressions example will be, you remove a lot of genes which no contribution to the process of this development. You only keep those ones contribute the most, explain your position of your cell in the development stage labels. Okay, so another problem will be how are you going to set up this cutoff? You can see, okay, I want to set up 0.05, and well, that really depends on the situation, what the problem you have. But in general, this is just description of what the regularization is. So in 2001, 2009, this several Stanford people, they come up with a lasso solution. This is called the list absolution G and the selection operator. So how this works, this just try to find a way to do this regularization and to select this beta values which are higher enough. Okay. So what they did is to add a error term in the loss function. So this error term is related to the L1 norm of the beta values. So remember, so that's the expression. So they put this extra term here. So this is called regularization term. Okay. So here, this is a beta value. So they use W as a variable name now, and you just take average, okay, for all the values. Then sum them together. So this is L1 norm, and you build that into your loss function. So now we can do the prediction to minimize the error, the epsilon between the difference between your prediction and the input. Okay, but also have to consider not make this too big. Okay, so we want to minimize this and also want to minimize this at the same time. So this term makes this loss function sensitive to those summation of the beta value. So if you have a lot of beta value be set into 0, then only keep those important ones. This term will be small, and at the same time you will also keep this error term small. Then altogether you get the the best solution for your loss function. If you don't have this regularization term, then you only care how prediction can make the correct prediction. You don't worry about the total values of effect coefficient, then you can end up with overfitting because you introduce a lot of this beta values into the equations. You solve this prediction very well and accurate, but by adding up extra unnecessary beta values in there. So this is the idea of lasso. I don't know if you get it. Let me know if you have a question, maybe in the computer session. So for all this regularization formula, you always see this term. Okay, so this is a prediction between your the difference between your prediction and the real, and this is this square. You always see a term like this. Lambda is a relative contribution of your regularization term will be. So in this case, lasso regularization will have using this L1 norm, so you have the absolute value of those. People also have a same idea, which is called a ridge regression. In this case, the regularization term is the dot product between these variables, coefficients. In this case, dot product is equal to this L1 norm, L2 norm. So this so-called ridge regression, another way to do this regularization. Okay, so if I write in the same way as the lasso expression, it was the L1 norm, but now it's L2 norm, with rigid regression, like this, okay? So how to understand the difference between them? So you have variables, coefficients, okay, the beta 1, beta 2. Just as an example, if you have a 2D, okay, so we see, okay, our regularization require the summation of beta 1, beta 2 has to be within this green box. That means the L1 norm of these two have been limited inside here. You can randomly choose all the solutions for your combinations of your beta 1, beta 2, but once you touch this edge here, you satisfied your solutions within this box, then you stopped here. So this box will give you the regularized solution. Although you can have a freedom to pick all the possible combinations, but those will be overfitting solutions. If you use L2 norm, which is a rigid regression, and you are dealing with a situation something like this, you allow the combinations of beta 1, beta 2 smaller than certain value, and that's within this circle, okay? Because L1 norm, L2 norm can be represented with this. All the values inside there will have L2 norm smaller than certain cutoff. So this is like you have this sphere or circle, try to cut touch the best solutions you can find, and the point you touch this ridge, H, is your solution, which close to the best solution, overfitting solution, but also satisfied your regularization combination requirement. So that will be your solution, which at this touching point. So you can feel in the hyperspace, if you have a sphere and you have this lasso L1 based this polygon, and you may have a slightly different flavors to do this regularization, and this will give you some kind of smoother solution because you found the touching point between your free solutions with certain point which satisfies the regularization. But this one, you have very sharp touching point. People also try to combine this both. So this is a lasso coefficient solution, and this is a region regression solution. This is the best place where, but there are overfitting problems. There's all the counter solution space. People also use the combinations of L1, L2 norm, and build this so-called elastic net regularization. So they all are usable, and you can use them to do this regularization, and in a way try to find the most important contribution coefficients. Okay. So there are packages you can use. I believe this is in R, and there are Python. There are MATLAB version as well. So this is a package named by the original author. This is a Python version, okay? So linear regression, you see this lasso is function, if you can see, very small, rigid regression. Okay, I have 15 minutes. I think I can finish half of this for the next section. Then we will continue another 15 minutes on Thursday lecture. So this is about, I believe it's very important to change your mind from this. Because in biology, you always try to find differentially expressed genes, or the gene upregulation. Okay. A lot of experimental designs end with a DE analysis to find the gene. Okay, upregulated, some downregulated. I'm happy with this if it fit my understanding of biology. If not, we just try different ways to set a cutoff until we found, okay, the terminology is good. That's most of your PIs probably will ask you to do. But in single cell, we really have to consider something else. This is variability of the gene expression, see whether it's important. We found it's very important. So sometimes even more important than those differentially expressed genes. Because those genes are the consequence of your regulation. You change your state of cells from, say, one stage to another, then you found the genes always express high in stage 2. But when you do this transition, when you do the regulation, the process is ongoing. Those regulator genes not always express very high. They contribute the function, and then they take a risk, take a rest. So not express for a certain period of time, then contribute again. So push the process go forward. So that's what we feel. The expression noise people normally see. Okay, in a single cell we have very noisy data. But this is the most important function, genes. So those are the example of the, especially you have a cultured cell. And you look at the cell, they all look very similar to each other. And the same cell type, no differentiation. In 2015, this professor in the UPenn, okay, Pennsylvania University, he proposed this so-called variation is a function of the single cell difference, single cell differences, okay, especially this single cell, okay. There are no difference, but their expression profile differed from each other. So see, he proposed this could be very important. This is a opinion paper. It's just a perspective, his own opinion. And the comment is a overview. But there's very little evidence because in 2015, the single cell data has not become abundant. The 10x Genomics introduced their device in 2016. And by 2017, there's more publications for utilizing those 10x Genomics controller to generate data. So when Professor Kim writing his paper, I believe he only have very few data points. So we put their idea into test because we have this system can generate a lot of cells, right? You see this many times. So we used several example data downloaded from a lymphoblastoid cell line, so the LCL. This is cultured in my lab of cells. We also download data from the endothelium cells. So this is these cells, epithelium, fibroblasts, dermal fibroblasts. So those are the three data sets we used. And there's another one I will mention what they are have to be on Thursday. So first, I use this lymphoblastoid cell line as an example. We look at the cells. So those are the cells, okay? Those are the genes. The matrix is much bigger, so this is only 200 genes as an example, but it's much larger. We first look at the cells in the G1 phase, SCA phase, and the G2 phase cell cycle. And you can see the yellower means the expression level is higher for those genes. The reason S phase and G2 phase look like the cell have a higher expression of overall, no matter which gene they are, because they are larger cells and there's more DNA, RNA in there. Okay, they are ready to be divided. So metastasis. Go. G1 phase cells, there are majority of cells in the G1 phase, but they are relatively small. I believe they are normal size. So we remove those cells in the S phase and the G2 phase. Only keep G1 phase cells. And we also remove these mitochondrial genes and restrict the library size to be in a very narrow region, okay, 50% to 95 percentile, and embed them into different, to see whether they're clustered, and then manually select. If you do PCA, TSNE, and FATE, you see even the homogeneous population of cell have a different representation in different embedding algorithm. So we picked this. Let's see. There another to do this. There's a new algorithm developed for doing this to combine different visualization and to get a so-called meta visualization. So if you pick some paper like this, you should be able to do your homework easily. Okay. So what we did to use FATE to look at the embedding projection of this to 3D. remember this lymphoblastoid cell lines, and they are basically they are B cells. Removed all the cell cycle cells, so only G1 phase. But still you see the arms and the structures, but we only use cells inside this base circle here. We want to look at the cell which is highly homogeneous. They are cultured cell, and when do the embedding, they all cluster together. So this is a group of highly similar to each other. The reason is we try to, based on this homogeneous population, to find a gene which express very differently between individual cells within this homogeneous population of a cell. Okay, the idea to find the noise gene. So if you look at this homogeneous population of cell and some genes like this RPS11, this Robertson protein small unit 11, the expression is homogeneous and it's very similar to each other. Well, this gene, if you look at the blue ones, they are 0, and they're highly expressed in some of the cell, but not other cells. So this is immunoglobulin heavy chain. This is one structure gene. This gene actually in the B cell development have gone through some resortment, the recombination. Some of the cells just have this gene. So that's where the noise come from. You only have some cells, because of recombination, random resorting, have that gene expressed. So you have high expression, but many cells have been recombined away from this gene. So if you look at the expression profile, and this gene expressed in all the cells, okay, but they have average probably 50 or 30. Well, this immunoglobulin genes expression, the magnitude is much higher than this, but there are a lot of zeros. Okay, you cannot see, but most of these are the zeros. But the average of these two genes are very similar to each other. All right, so the average of this is almost equal to this. But this one contains a lot of zeros. But this gene expressed in every single cell. So we compute coefficient of variance, and you can see, okay, this is really large. This is standard deviation divided by mean. And this is small. They have a similar mean, but one have a very huge variability. So one cell expresses it, but 600 times. Another not expressed. Another maybe 500 times. So that's create a very, very noise expression of this gene. Well, for the housekeeping gene, like Robertson genes, you just have to have certain level, and always the same. Okay, now it's a regression. So we put these two genes in this CV against the mean, and this is log-log. And these two genes have a similar mean, right? So they are very similar to each other. But you have a CV, which one is much larger than that. So this will be the Robertson protein. This will be that immunoglobulin, have a much higher CV. So there's two genes here. But if you put all the genes together, you will see this distribution. Okay. The gene mostly with high expression will have lower CV. Those genes express average less than have a high CV. So this is a regression. Okay, we did a regression. Also, this is log-log. So the theory we mentioned, this should be a straight line if you have a Poisson distribution. But we fit with this nonlinear regression using this square. So this green line gave you the prediction. If you have this level of average, you should have this level of the CV. The mean and the CV should be expected, should be predictable. What we are interested in is the difference between the observed. So for this gene, for example, you have average, which is here. You're supposed to have a CV right here, right? Because you have regression green line. But in reality, in the real observed data, this gene have a much higher CV than expectation. It's jumped to here. So this is another example which have really high unexpected CV with regard to the average expression, because if you follow all the genes populations, this is all the genes in the data, it's supposed to be on this green curve. But those genes have an extremely high residual CV, so the expected observed minus expectation. So those genes are the highly variable genes we select for. Okay. I think I stop here, and I will continue Thursday and see what are those genes. So turn out that those genes are the most important in terms of function. So that's the way you can use regression to find those genes which have an unexpected level of higher than average, than normal CV, which this CV is a residual CV which already controlled by the average, regressed out the average. Okay. All right. See you Thursday.